Hi, my name is Pranil Kapadia and welcome to a presentation on gears. Okay, so first a little introduction to gears. Gears are pretty much wheels with teeth. They're used in many mechanical devices to make things turn, and they transform motion or power from one moving part to another. Spur gears are gears in the same plane that move opposite of each other because they are meshed together. Here we have two spur gears connected together. In this case, the gear on the left is the driver because it is turned by a motor. It begins to turn the gear on the right, which is called the driven gear. Before we begin solving questions involving gears, we must first determine the key terminology. The point where the gear teeth actually touch is known as the pitch point. Pitch circle D sub P is the circle centered on the gear axis passing through the pitch point. Note, the module is the ratio of the pitch circle to the number of teeth. Now we have the circular pitch. This is the curvilinear distance measured on the pitch circle from a point on one tooth to the corresponding point on the next tooth. This is given by the equation below, where n is the number of teeth. Base pitch, P sub B, the curvilinear distance measured on the base circle from a point on one tooth to the corresponding point on the next tooth. The diametral pitch is the number of teeth on the gear per unit of pitch diameter. Note that the inverse of the diametral pitch is the module. The addendum circle passes through the tips of the gear teeth and the dedendum circle passes through the base of the gear teeth. The addendum is the radial distance from the pitch circle to the top land of the gear, essentially the tip of the gear teeth. The dedendum is equal to the radial distance from the pitch circle to the bottom of the land tooth. The whole depth is the sum of the addendum and the dedendum. The line of action is the line along which the force between two meshing gears is directed. In general, the line of action changes from moment to moment during the period of engagement of a pair of teeth. For involute gears, the tooth-to-tooth force is always directed along the same line. That means the line of action is constant, as seen by the animation on the right. The pressure angle is the acute angle between the line of action and a normal line to the connecting gear centers. This is given by the symbol phi. Okay, now here we have a graphical summary of all the key terms just described for clarity. Another important term is the contact ratio, which is the average number of tooth pairs that are in contact through the gear cycle. Okay, there are a lot of equations used in gear analysis, so here is a summary of all of them. Okay, let's do an example. Find the module and the pitch diameter of a standard gear whose circular pitch is 37.7 millimeters if the gear has 36 teeth. Okay, so going back to the equation sheet previously, we can use this equation and rearrange for the pitch circle dp. Now we simply sub in 37.7 millimeters and the number of teeth n, 36, which will give us 432.01 millimeters as our pitch circle. Okay, example 2 says determine the module of a pair of standard gears whose center distance is 58 millimeters and the gears have 18 and 40 teeth respectively. Okay, so from the equation sheet given previously, we have the following relationship. Now we're letting C equal 58 millimeters. The sum of the two pitch circle radii will equal C. And then rearranging to get rid of the pitch circle for gear 1 to solve for gear 2, we get that the pitch circle for gear 2 is 80 millimeters. Then substituting back into the original equation, we find that the module is 2 millimeters. Okay, now we move on to gear systems, which includes gear trains and planetary gear systems. Simply put, a gear train is a combination of one or more gear pairs. A simple planetary gear drive is shown by the animation on the right. Planetary gears are typically made up of the following: a sun gear, a planet gear, a planet carrier, and an internal ring gear. Okay, here's example 3. Assume that gear 2 is driven at a speed of 60 rpm in the counterclockwise direction viewed from the right end. Gear 4 meshes with a fixed ring gear and with gear 5. Okay, cut. Okay, here's example 3. Assume that gear 2 is driven at a speed of 60 rpm in the clockwise. Okay, here's example 3. Assume that gear 2 is driven at a speed of 60 rpm in the counterclockwise direction viewed from the right end. Gear 4 meshes with a fixed ring gear and with gear 5 as shown. Find the magnitude and direction of the angular velocity of gear 5. There are three gears that can rotate. There are three gears that can rotate about the fixed axis in the system. We include gear 7 in this list, but ultimately we'll use the fact that its velocity is 0. There are three gears 2, 5 and 7, that can rotate about the fixed axis in the system. We include gear 7 in this list, but we'll use the fact that its velocity is 0. We will solve the problem by writing relative velocity equations for all the gears that have shafts that can rotate in fixed bearings. After rearranging, we have the resulting equations. The angular velocity of gears 2 and 5 relative to the carrier is as follows. Similarly, the angular velocity of gears 2 and 7 relative to the carrier is. Now if we equate the two equations with the equations above, we get and this. We know that omega 2 is 60 rpm and omega 7 is 0. With these known values, only omega c is unknown. Substituting the known values into the equation, we get, and solving, we get that omega c is 10.862 rpm. Now given omega c and omega t, we can solve for omega 5. Substituting the values yields omega 5, which is 52.137 rpm. Thank you for watching this presentation on gear systems, and I hope this helped you out with your revision. Thank you.